Yeah, thank you. Okay. So, hello everyone, and welcome to this webinar to be delivered by Dr. Cesar Ceballos from TU Graz, Austria. Before beginning this webinar, I would like to mention a few things. So, if your connection is lost, then you can try in joining the Zoom link again. But if that is difficult, then you can watch it on our Facebook channel, and the link will be shared in the chat in some time. Uh, you can use the chat options to send questions to either me or to Manjil, preferably to me because I'm the moderator for today's webinar. And now I will introduce today's speaker. So today's speaker is Dr. Cesar Ceballos from TU Graz, Austria. He's a postdoc at TU Graz. He obtained his doctoral degree in 2012 from Free University Berlin, Germany, under the supervision of Gunther Ziegler. He then worked as a Banting postdoctoral fellow in York University, which is the Government of Canada's most prestigious award for postdoctoral research. He was a visitor member of the Fields Institute in Canada and then a postdoc at University of Vienna, Austria, where he obtained his habilitation degree in May this year. He works in discrete geometry, polytope theory, algebraic enumerative and geometric combinatorics, Hopf algebras, diagonal harmonics, representation theory, and tropical geometry. So over to you, Cesar.
Thank you very much for the nice introduction, and thank you very much for the invitation. This is a pleasure for me to give this talk. So today I will be talking about the geometry of a robotic arm in a tunnel, and this is joint work with Federico Ardila, Hanner Bastidas, and John Gu. Okay. So before talking about this, let me start by a nice problem. So suppose you are a snake and you want to hunt a frog. Okay. And then you ask yourself, how can I reach that frog as fast as possible? Or how can I move from one starting position to another one in the most optimal way? So in real life, if you are the snake, you of course will not ask this question yourself, but you just follow your instincts and just start moving until some point you catch that frog. Okay. So this is the kind of questions we will be working on this today. And let me start with a toy example. So let me start with this frog in position 1. And the question is, how can I reach position 2 in the most optimal way? Okay. So at the beginning, your snake is a little bit kind of stuck. So you can start by moving the tail. And then you start moving a little bit the body of the snake. Then you move the head. Then you move the body again. You move the body again. You move the tail, and then you reach position 2. So in total, I did it in 6 moves. And I want to ask you, can you do better? So I just want you to try for a couple of seconds. Did anyone do it in less steps? So in general, this is not a simple question. So this is a simple question to understand, but it is not in general simple to answer. And in this talk, we will solve a similar problem, which is about the optimization of the motion of a robotic arm moving in a tunnel. Okay. So this is the kind of robotic arm we are interested in. So it's very similar to a snake, but now we are fixing let's say the tail of the snake or the beginning of the arm at the lower corner of your tunnel. So you should think of this as an arm that is moving in a tunnel and it's affixed on the lower left part. Okay. And this robot can move according to certain rules. So it can move a joint. So can you see me actually? So you can move a joint like this. Or you can move the hand like this. Okay. So these are the 2 examples. So you can move the joint like this or the hand like this. And here are 2 examples. So for example, here I'm moving in this little part over here, the joint. And in this part here, I'm moving my hand. Okay. And of course, a natural question is, how do you move optimally from one position 1 to a position 2? So I want you again to try to think about this question for a couple of seconds. So let's say I want to move this robot from this position to this one. And actually it is not quite clear how to proceed. So let's say I can start maybe moving this joint over here. Maybe that one joint over there, but then it gets kind of tricky. So you don't really know right away what to do. So let me start with a simpler question. So, and this question is, how did I come to my office today? So this morning I woke up, I took a shower, I had breakfast, I talked to my family, then I took public transport, and then I get off at one station that is located at a place called Kaiser Josefplatz. And from there, it got kind of tricky because I had to walk to the institute. And in order to walk to the institute, there are several paths you can take. And the question is how do I take the optimal path to get there faster? And one possible answer is you use a map. So you look at your map, you have one position 1, one position 2, and this map will tell you this path over here is the most optimal one. Okay, this is a very simple idea, but it's really powerful. So we will do the same for a robotic arm. Okay, so we will construct the map of all possible states of the robot. So let me go back to my toy example. So a snake that wants to move from position 1 to position 2. So what I will do, I will just draw all possibilities of the snake, and I will like join two possible states if you can move from one to the other by applying a simple move. Okay. So here's the map of all possible states of the snake. And if you want to move from position 1 to position 2, you forget about the snake, and then you just look at this map, and then you say, I need 1, 2, 3, 4, 5, 6 steps to go from position 1 to position 2. But now you can do it in 2 different ways. I can go 1, 2, 3, 4, 5, and 6. And actually, if you look at this little square here, so I need, again, 6 individual steps. But if you look at this little square here, this is kind of funny. So let me look at this closer. So here's this little square. And if you look there, you have 2 possibilities to go from one corner to the other. Either you move the head first, and then the body, or you move the body first, and then the head. But actually, you can do these 2 moves independently at the same time. So in the map, this corresponds to filling this square. So you should think of this as, I want to go to my office, I get to a park, and I want to go from one corner to the other. So I can either go around the park this way, I can go around the park this way, or I just cross the park diagonally. Okay, so in the map, this corresponds, so this performing these 2 steps simultaneously corresponds to filling the square in the map. So my map will look like this. And now if I allow these 2 independent steps to be performed simultaneously, I will just need 5 moves to do it. So I will do 1, 2, 3, 4, and 5. Now here is my map for the robotic arm of length 4 in a tunnel of width 2. This has a really nice shape. And you continue, and here is a map of a robotic arm of length 6 in a tunnel of width 2. And this map has a structure of a cubical complex. So for example, you see here a 3-dimensional cube, and this corresponds to 3 possible moves that you can perform independently. So in general, if you have D independent moves that you can perform at the same time, this will be a D-dimensional cube. And of course, the question is, how do we understand this map? And most importantly, how do we navigate it? And of course, there are many difficulties that occur. One of them is that this map has too many vertices, and also it has a really big dimension. And the way to navigate it, for that, we will use techniques from geometric group theory, namely cat-zero geometry. Okay, so let me introduce some preliminaries. So cat-zero spaces. So a map or a space is a cat-zero space if for any 2 points in your map, there is a unique path of minimal length between these 2 points. These paths of minimal length are called geodesics. And second, you need that this space has non-positive curvature. So if you have a triangular in your space, you want this triangle to be thin, which means that if you have 2 points in your triangle, the distance between these 2 points is smaller than or equal to the distance of the corresponding points in a triangle in the plane. Okay. So let me explain that in an example later. But now a cubical complex is just a space which is obtained by gluing cubes of possibly different dimensions along their faces. And this is an example. And we are interested in cubical complex that are cat-zero. So let me go to this cat-zero property again, and let me explain it by an example. So let's say you have 3 unit squares that are glued around a corner. So this is your space, so these 3 squares. And I ask yourself, is this cat-zero? So in order to check if something is cat-zero, you need to check if the triangles are thin or they are fat. If they are thin, your space is cat-zero. So let's take a triangle. So let's take points A, B, and C that are at distance 1 of each other. Then you draw a triangle in the plane with the same distances, 1 of each other. And then you take 2 points in the edges of your triangle, and then you measure the distance between them. So in this case, you get that the distance between D and E is bigger than the distance between D prime and E prime, the corresponding points in the triangle and the plane. And therefore, your triangle is fat. And in fact, you see that this triangle is kind of fat. So your triangle is fat, so this space is not cat-zero. So let me now make another example. So let's suppose you have these 5 squares that are glued around this corner. And again, you ask yourself if this is cat-zero. So again, for that, you need to understand the triangles. So you look at this triangle and you ask yourself, is this triangle thin or is this triangle fat? So I will say that this triangle looks kind of thin, and indeed this is the case. So for example, if you take these 2 points, D and E, and you take the corresponding points D prime and E prime in the triangle in the plane, the distance between D and E is smaller than the distance between D prime and E prime. Okay, so this triangle is thin and your space is cat-zero. But actually, I'm kind of cheating here, because if you want to check if a space is cat-zero, then you need to check that the distance between any 2 points D and E is smaller than the distance between the corresponding point D prime and E prime. I just checked 2 points in this example. If you want to do it in general, you need to check all the points. But not only that, you need to check all the triangles. So in general, to check if a space is cat-zero is not an easy task. But for cubical complex, there is this really nice result of Gromov that says that a cubical complex is cat-zero if and only if your space has no holes, so it is simply connected, and it has no empty cubes. So this is really nice because you don't have to measure anything. It is only about the topology of your space. Okay. And there is a really nice combinatorial characterization done by Ardila, Owen, and Sullivan that says that cat-zero cubical complexes are in corresponding with certain combinatorial objects that are called PIPs. And these pips are really nice because they can be used as remote controls to move your robot optimally from one position to another. Okay. So instead of telling you the details about these results, let me tell you how to construct this pip, and let me tell you how to use it to move your robot.
There's a question.
Yes.
So, why the name Cat Zero? What was the reason behind the name Zero?
Oh, I knew this, but I forgot. I need to check it out. Okay. But it has to do with topology of these spaces.
Anything to do with category theory?
And no, I don't think so. But there are also, like, for example, CAD1 spaces, CAD2 spaces, and so on.
Okay.
But,
thank you. Yeah.
But it's a notion that comes from topology.
Okay, thank you.
Okay. Any more questions?
No.
Okay. Okay, so let me tell you now how to construct pips and how to use them. Okay. So here's an example. So let's say you have this map on the left, and you want to construct the remote control pip in order to move or to navigate this map. Okay. So we will construct it as follows. So the elements of your pip, these points over here, will correspond to the cuts which split cubes into halves. So this will be these cuts over here. So cut 1, cut 2, cut 3, cut 4, cut 5, cut 6, and cut 7. And given two cuts I and j, we will declare I to be below j if one needs to cross the cut I before crossing the cut j. Okay. So for example, so let's assume you have a route in your map. So you start over here and you want to cross, in order to cross hyperplane or cut number 2, you need to cross 1 first. In the pip, this means 1 is below 2. If you want to cross hyperplane 3, of course you have to cross 2 first. So 2 is below 3. And similarly, 4 is above 3. So 3 is below 4, because you need to cross 3 before crossing 4. But you can cross 5 before crossing 3. So 5 is not after 3. They are uncomparable. Okay. But if you want to cross 6, you need to cross 3 first. So 3 is below 6 in your pip. And also 5 is below 6 in your pip. And 7 is above everyone, because you need to cross all the cuts in order to be able to cross 7. Okay. Is this clear? Okay, excellent. Now, the nice thing about these pips is that the vertices in the map are going to be in bijection with other ideals in this pip. So let me explain that by an example. Yes?
Yeah, Cesar, I will break you here. I'm assuming you're using the notion of Hasse diagrams of posets here, right?
Yes.
So can you just mention what they are for the audience?
Yes. So the pip will be a partially ordered set. So it consists of some elements, which in this case are the cuts. And you can draw the Hasse diagram of a poset just by drawing a line between two elements. Let's say 2 is below 5. But you just draw the lines that are necessary. So for example, 2 is below 7. So you need to cross 7. You need to cross 2 in order to be able to cross 7. But I will not draw that edge between 2 and 7 because it kind of follows from the fact that 2 is below 5, 5 is below 6, and 6 is below 7. Okay, so in order to draw a poset, you can draw it by just drawing the elements and just by drawing the necessary conditions. So like the cover relation. So 2 is below 5. It's a cover relation if there is no element set, say between 2 and 5. So that's the Hasse diagram. And that's what I'm drawing in this picture. Does this answer your question?
Yeah, thank you.
Okay, excellent. So in this picture, 2 is below 7 also. Okay, so let's try to navigate this map. So let's say you start with your snake in this position, and then you want to cross the cat number 1. So you mark this element of your PIP 1. Now you cross the cat number 2, and then you mark the button number 2, or you place the button number 2. Then you cross the cat number 5. This corresponds to pressing the button number 5. Then you cross the cat number 3. This corresponds to pressing the button number 3. Then here you get into the corner of a park, so you can cross the park diagonally. So you can cross the cats number 4 and 6 simultaneously. And it corresponds to pressing the buttons 4 and 6 simultaneously. And then you can continue playing. So here you uncross 6. So you press button 6 again. Here you uncross 4 and 5. Then you, let's say, cross 5 again. And you cross 4, 4 and 6 again. And then you cross 7. Okay. And if you want to characterize the sets of buttons that are pressed, these are called order ideals. And what is an order ideal is a set of points in your PIP such that if you have a point that is pressed, everything that is below it has been pressed as well. And this makes complete sense because if you want to press 7, everything below 7 needs to be pressed, because in order to cross the hyperplane 7 or the cat 7, you have to cross all the other hyperplanes before. Okay. Okay. In general, like there are some cases where you can cross a hyperplane, and if you cross, let's say, hyperplane 3, you cannot cross hyperplane 5 anymore. So there are some inconsistent pairs. So in general, so you have order ideal without inconsistent pairs. Okay. So now the message is that the PIP is very useful. And the advantage of working with this PIP or remote control is that they are much simpler than the map itself. So let me give you an example. So this is an example of the map of a robot of length 7 and width 2. And this was drawn by one of the students in this project, and he was actually running out of paper. So he had to glue several pieces of papers together in order to be able to draw this map. And you see that it starts getting really complicated, and this is only about length equals 7. If you try to draw this one over here, this is of length 2, 4, 6, 8, 10, 12, 13, you will get into troubles. So it gets really huge, and you will see cubes appearing of really high dimensions. So it gets really complicated. But if you play with this for a while, and then you try to understand its PIP, it turns out that the PIP, it's much simpler. So it's still big, but at least it's 3-dimensional. It has a really nice kind of fractal looking structure, and you can draw it and you can understand it. So we were able to completely characterize these PIPs for these robotic arms. And the elements of a PIP can be described combinatorially in very simple ways. They are given by some combinatorial objects that look like coral snakes. And these combinatorial objects also have a number attached to them, S, which satisfies some conditions. And we can describe the order relations of these snakes. I don't want you to focus too much in the details. It's most importantly, you can use this PIP to prove this result, that namely that the space of the robotic arm is a cat-0 cubical complex, and you can use this PIP as a remote control to move it efficiently. So there is an algorithm implemented in Python to move your robot efficiently, and let me show you this in an example. So here's how the program works. So you give the initial position of your robot, let's say encoded by some, so here R states for right, then up is A, like an U it means like an up step, and then D means for a down step. So you can give a position 1 and a position 2, and the program tells you what's the minimum number of steps you make, where you allow like independent steps to be done simultaneously, and the minimal number of individual moves is, like in this example, 94. And it also shows you a video how to go from one position to another. So this was the example I presented you at the beginning of the lecture. So this is really nice. So after finishing these results, I did organize a science club for mechanical engineering students in Colombia about mathematics and robotics. And there were many really smart students that got interested in this project. And among them was Arlys Asprilla, that also had some experience already in constructing robotic arms. And he got interested in this project, and he went ahead and make a CAD simulation of how we should construct this robotic arm. So he was explaining to us how to do it in reality. And this is his video. So he was explaining, okay, you need to use some kind of motors and you need to use these materials and you should do it like this. And this is his simulation. And this is how the robotic arm should move. And actually, he did not just stop here. He actually went ahead and actually constructed a robot for us and was implementing the code. So here is how the robot looks like. This is a really nice robot. Okay, thank you very much. Are there any questions?
Thank you, Cesar, for the wonderful talk and the lovely animations. And so now I'll ask a few questions. So one question is, what is the geometry where triangles are thicker? Is there any application for that geometry?
Can you repeat that?
So actually, this question is from Manjil. So maybe if you can unmute and ask that.
Yeah, so you showed the geometry where the triangles are thinner than in the plane.
Mm-hmm.
What about the other geometry where it is thicker than in the plane? Is there any such nice applications for that?
So these people in geometric CAD theory are explicitly interested in the spaces where the curvature is non-positive. So they are really interested in the spaces where the triangles are thin. They do not study the case where the triangles are fat. And I do not know about an application on that case. But there might be some, but I don't know about it.
So another question is, what about moving in more dimensions? Is something known about that?
Yeah, you can also try to do a robotic arm in 3 dimensions. And the problems that we reach there is that the space is not cat zero. So we cannot actually use these techniques to approach that problem. But let's say like if you are like, I don't know, like constructing a tunnel for a train, you can kind of assume that that tunnel is 2-dimensional because the robot is moving there. So it might be that this project might have some applications, or some similar projects have also some applications by considering just a 2-dimensional case.
So did you mention that the PIP is a 3-dimensional complex?
Yes.
So is this for the specific case, or is this in general?
For this specific case.
So here, the size of the, so for this particular width of the tunnel, or for even if you increase the length of the tunnel, you're going to get a cubical.
So the length of the tunnel is arbitrary, and also the width.
Okay.
So the length of the tunnel will give you some kind of the height of this picture, and the width will give you how bright it is. So it will move in that direction.
Okay. So this is general question we ask all our speakers. So can you mention some applications of this theory?
Of this theory. So if you want to construct real application, like if you look at people working with robots in reality, these spaces get really complicated. And actually there are other techniques to move them. I think this is a little bit far from real applications, but the mathematical background is already really powerful and might be of use in the future. I'm absolutely sure of that. But real applications at this moment, I think we are far from that, because these spaces get really complicated really quickly. So if you want to construct a robot moving in your house, doing something, then these spaces get too complicated.
So what are sort of like the proof techniques that are used in this thing, that the connection with pips, and also uh, the coral snakes?
Yeah. So this is like purely combinatorics. And essentially you just have to sit down, look at these maps for a long time, do lots of examples, and try to understand how the cats look like, and then get some inspiration from heaven or somewhere, and then try to understand these pips, and then you at some point you get with this idea that they should look like this. But it requires a lot of playing with these maps. Yeah.
Uh, so another question is, you mentioned that you worked with several students as part of this project.
Yes.
Can you mention something about that, and how it was? And because a lot of our audience is undergraduate students, maybe.
Yeah, actually, this is a really nice project, and the two main contributors of this project are actually, or were actually, two undergrad students. One of them was an undergrad student in Colombia, who is the one making all these pictures, and he was actually the one like playing with these maps a lot. And we were kind of using his pictures and his intuition to try to understand how this works in general. But this was actually his undergraduate thesis to work on these maps. And the other student is John Guo. So the first one was Janer Pastillas, and the other one is John Guo, who was a student in San Francisco State University. And he was the one like programming all this stuff. So he was the one doing this Python code and these animations. Yeah. And the other ones, like these ones, are also undergrad students. They are mechanical engineers, and they were participating in this science club that I was organizing. So all the students in this project were undergrad students at that point.
So, so what kind of background did they need before beginning to work on this project?
One of the nice aspects about combinatorics is that you don't need a lot of background. You can understand these questions really quickly without knowing too much background. So they can start working on these projects right away. Like, of course, if you know a little bit of topology and you have some experience in combinatorics, in counting, then you get a lot of tools to approach these problems a little bit faster. But in principle, the students did not know anything of background regarding these problems when they started to work on them.
Yeah, that's really amazing. I mean, you can, because certainly the videos are really they're really amazing, right? And the programs with the animation, and then going ahead and building a tunnel that really looks really amazing. And it's amazing that one can get into this without uh, like studying a lot of theory and then.
No. Yeah.
So, did you use some tools from like in your proofs or in the theoretical work? Do you use anything from mechanical engineering or from robotics?
No.
Okay. And actually, we'll think we're almost out of questions. There's one general question. Uh, so, can you mention some books which or survey articles or books which one can use to get into algebraic and geometric combinatorics?
I think one standard book in combinatorics is a book of Richard Stanley, who is a famous professor in MIT on enumerative combinatorics. This is a beautiful book. And about geometric combinatorics, there are books like of my advisor Gunther Ziegler that is talking about geometric objects. And there is a lot of geometric combinatorics in there. This is called Lectures on Polytopes. And about cubical complexes, I know like papers, but not really books about this topic. But in combinatorics, there are lots of beautiful problems, and this book of Stanley is a very good source.
So thank you very much, Cesar. I think I don't think we have any more questions. So now, yeah. So Manjil, do we stop the recording now? Streaming.